Recently, there's been an increased interest in the way a contagion propagates in space and time throughout a network of connected individuals. However, for at least a century, mathematical models have been proposed to describe the spatial-temporal dynamics of diseases, and for many decades, mathematical models have been simulated on computers. I have simulated computationally some classic epidemiological models on a lattice, with all individuals in fixed positions, with neighbors in fixed positions. This one is an SI model of an incurable disease, infecting all susceptible individuals. You just need one infected individual and a positive transmissibility, and the disease spreads everywhere. Not surprisingly, if transmissibility worsens, the contagion spreads faster. We see a clear relationship. Also, the closer patient 0 is to the center of the lattice, the faster the disease propagates throughout the entire population. The dynamics of the infection is clearly described by a logistic equation. Suppose a good proportion of the population is immune to the pathogen. They do not contract or transmit the infection. The resulting contagion may die out before infecting all susceptible individuals, even if the disease is incurable, and every infected individual transmits the disease to all their non-immune neighbors. In this example, a random 40% of individuals are immune, only 10.5% get infected, almost 50% are susceptible, but are protected by herd immunity. Although the model is an oversimplification of reality, it's still relevant in a time of pandemics, lockdowns, physical distancing, vaccination campaigns. In our 150 by 150 lattice, irrespective of transmissibility rates, a little more than 40% of immune individuals effectively protect the entire population. This is an SIR model. There are susceptible, infected, and removed individuals. The model describes deadly diseases or curable diseases with acquired immunity. Upon dying or acquiring immunity, an individual is removed as they cease to be a carrier of the pathogen. In this example, the transmissibility is 30% and the lethality is 40%. The disease is incurable. As infected individuals die fast before transmitting the disease, the contagion eventually dies out, which sort of sounds counterintuitive, but it's quite logical upon reflection. Nonetheless, in this example, almost 44% of the population gets infected and die. In a sense, the protective mechanism is analogous to that of herd immunity. There is a thin yellow line separating community safety from hecatomb, annihilation. Another interesting model is the SIS model, susceptible, infected, susceptible again after recovering from the disease. Once recovered, individuals are again able to contract the infection and transmit it to their neighbors. Unless the recoverability rate is much faster than the transmission rate, the pathogen is bound to become endemic, and the prevalence will likely end up fluctuating around some constant value. Clearly, there is a great deal of complexity in the possible outcomes. Still, if the recoverability is much higher than the transmissibility, the contagion is likely to die out. Again, there is a thin line between eradication and endemicity of the disease. In this example, susceptible and infected individuals fluctuate respectively around 70% and 30%. The stochastic process will keep going on forever. I made these and other simulations using R, a free statistical software. The first step in simulating these models is to set the parameters that determine the dynamics of the system. Let's start by setting the probability of transmission upon exposure to an infected neighbor after one iteration. Let's make it 5%. Then let's set the dimensions of the lattice, for example, a 15 by 15 square. Generate a 15 by 15 logical array where each cell is false, meaning that no one is infected yet. This is what the lattice initially looks like. Now choose an individual on the lattice as patient 0 and assign value true to its element in the contagion matrix. This individual has now contracted the infection. Now let the contagion begin. First, identify patient 0's close contacts. For each of these, generate a uniform random variable between 0 and 1. If less than p, the neighbor contracts the infection and its cell is assigned value true. At each iteration, repeat for every infected individual, and the contagion will eventually spread everywhere. Analogous methodologies are adopted to simulate the models we watched before. Simulating a model allows you to visualize how the model behaves. It boosts your intuition of the underlying complex phenomenon. You identify statistical regularities and patterns, make predictions on events and their likelihood, and you become aware that counterintuitive things may happen which you hadn't expected. Contagion propagation models are not only used to describe the spread of an infection within a population, They can also provide insight into the spread within a community of ideas, opinions, behaviors, innovations, gossip, fashions, or the spread of financial shocks within an economic system.